Na bolsinha da frente, assim, não tinha zíper nem nada.
Mas o exercício físico pode ser uma boa.
Acho que ele não foi comer lá. Ele foi comer aqui. O que devia ter ajudado, né? Tudo aqui. E geral as pessoas são brother aqui também.
Okay, so good morning everybody. I think we are still missing a few people. They are already too late, so we're going to start out. Well, we start with the easy problems anyway, so shouldn't be so bad for that. Yeah, okay. So let's go straight into action. Let's start with the easiest problems of yesterday's contest, and we'll see what happens afterwards. So, probably the easiest problem with wallpapers. We are given some kind of a story about different stores that sell wallpapers of different dimensions. Essentially what it boils down to is that each store can be represented as a rectangle in the plane with axis aligned sides. So we have a collection of rectangles. And the question is whether there is a rectangle like this one or not. So a rectangle that contains inside it all of the remaining n-1 rectangles. The number of rectangles is too large for us to try all possibilities or possible candidates and verify them, but luckily this shouldn't be needed. Why is that the case? Well, there are multiple approaches how to solve this in linear time. For example, you can make the observation that if there is a solution, then the largest of all the rectangles has to be the solution. So you just scan through all the rectangles, find out the maximum area, and then verify whether or not this particular rectangle has the property that it contains all the remaining ones. Another linear solution would be that you can scan through all the rectangles to find the minimum and maximum x coordinate among all of them, the minimum and maximum y coordinate among all of them. This gives you the exact dimensions of the rectangle you are looking for, and then you do a second pass and check whether such a rectangle is present. So there has to be a rectangle that has all four coordinates at the same time. You would have just a single one like this, and the second one like this, and this one wouldn't work because this is this, and vice versa. So, very easy task, solvable in linear time. The second really easy problem was a problem about packing gifts. And in this problem, we have two types of items. One collection of items are the gifts. In the other collection of items are the packages. I'm not sure which is which. Let me check. Okay, so it was given that the items have sizes 1 through n. For each size there is exactly one item of this size. And the boxes have an arbitrary sizes between 1 and n inclusive. So you are given this sequence of the sizes of boxes. And what you are asked to do is essentially to count the perfect matchings such that each item fits into the corresponding box. So we have to place items in the boxes, one item per box, and each item has to be smaller or equal to its own box size. The thing to note about this problem is that n is really, really large, something about the lines of hundred thousands of a million. And in this case, you know that we are looking for an efficient solution. So you cannot just afford to generate all possibilities, you have to find an efficient way of counting many of them at the same time. And usually the pattern, how such a solution can look like, would be that you have to start in some systematic way. We'll not start from the middle, but you can start from the smallest items, or from the largest items, or from the smallest boxes, or from the largest boxes. And usually some of these approaches will work. Not all of them, but some of them it will turn out to be the case that there is a place where you can make some kind of sequence of independent choices. Because as long as you can make a sequence of independent choices, then the answer is very easy, because you just multiply the number of choices you have in each of those steps, and then you have it. So what happens here is one good place where to start solving this problem is from the largest item. The largest item is size n, which means that it can only fit into boxes of size n. So we can take a look at those boxes. If there are no such boxes, we immediately know that the answer is 0. If we have more than one, then we can choose either of them. So all of these choices are valid. And even more, what will happen? Regardless of which of these boxes we choose, always we are left with exactly the same situation. We remove one of these boxes from the equation. So in this first step, when we are packing this particular item, the number of choices we have is the number of boxes of size n. Next we move on to the second largest item of size n-1. What happens now? Now also the boxes of size n-1 become available. We can already use those, or we can use any of the remaining larger boxes. And again, for the rest of the solution, all of these boxes are indistinguishable, because each of these boxes can be also used to store each of the items we will be processing in the future. So again, we do the same thing. We increment the count of available boxes by all of the boxes that have size exactly n-1, and then we can choose any of the available boxes. So we multiply the current number of solutions by this new number of choices, and regardless of which one that we choose, this just decrements the number of available boxes for the future by 1. So this is the entire solution. Now let's move to the next item, add new boxes, and multiply the current count of solutions by the number of options we currently have, and then decrement it by 1. If at any point you run out of boxes, you will multiply by 0, so you will automatically get the answer 0. You don't have to handle this as a special case. So, to summarize, we started at the end to look for the solution in a systematic way, and we discovered that it happens to be the case that if we go from n down to 1, the choices kind of are all the same. In each step we have multiple options, but all have the exact same effect. So we can just multiply it and get the result. Okay, all clear? Let's go on. The next easy problem is a problem about defending the fort. We have a fort that looks like this. The shape actually doesn't matter in terms of solving the problem. The shape only matters to the defenders who are stuck inside and trying to survive. So for each of the walls, we are given the number of attackers that are coming in, and we are given a coefficient, Ki, that tells us that each defender who is placed on this wall can kill up to AI, up to Ki incoming attackers. So some of the walls are easier to defend, a single person can fend off multiple attackers, some of the walls are harder to defend. And the task is that given the numbers of attackers that are coming from the outside, and given the number of defenders we have inside, what is the maximum number of attackers we can kill by distributing these defenders? And it should be quite obvious that the problem can be solved repeatedly, because each defender can get, if we can imagine the entire process like this. So we not only distribute the defenders to the sides of the fort, but also we group them together with the attackers they are going to kill. So here we will get a single defender with some attackers, a single defender with some attackers, and maybe this side already ran out of attackers, so here's a single defender that has the 2 remaining attackers. And now, whenever you have a final configuration and you claim that it's optimal, then it must be the case that you cannot shift, you cannot remove any single defender from one wall to another. So for example, if there would be another wall here with K equal 3, and there would be still a lot of unblocked attackers, then it would be better to move this defender from here to there, because here he only has 2 attackers and here he will block 3. So it turns out that we can assign the defenders to the walls greedily, starting from the places where the defender will kill the most attackers. The only problem is that all of the numbers are quite large, so we cannot afford to do this one person at a time. We have to do it in a faster way somehow. So the most straightforward implementation of this solution looks as follows. We will simply take the information about all of the walls. So for each wall we will have a record Ki, AI, and we will place all of these into a priority queue. So we will order these records primarily according to Ki, which is the number of attackers a single defender can stop, and secondarily after this, but this doesn't actually matter. And now the entire solution will be a single while loop, while we still have some defenders. Pop the best option from the priority queue. Use as many defenders as you can. So for example, if a record like this would be 10 and 137, what will actually happen is that this means that you can have 10 defenders kill 13 attackers each, and then there is a single defender who can kill the 7 remaining attackers. So if you are processing this, there are 2 options. One option is that the remaining D is less than or equal to 10. If this is the case, then you simply assign all of the remaining defenders here. Each of them will kill 13 attackers, and that's it. If you have more than 10 defenders, what you want to do now is you only want to use this option. You don't want to use this option yet, because there may be a better way of spending the last person than killing 7 attackers. There may be another wall where the same person could kill more than 7. So what you do now, if D is greater than 10, you will only use 10 of the defenders, each of them killing the 13 people, which is the current best you can do. You decrement D by 10, and then you reinsert a new record corresponding to this. So the new record will be simply 7, 7.
You changed the numbers. 13 defenders kill 10.
Yep. That is correct. Yep, it should be like this. Thanks. So if we have a single remaining person who can only kill fewer people, then we will process it later simply by leaving it as a remainder and reinserting it into the priority queue with the correct constant, so that this tells us that there is a single person who can kill 7. So in this way, we continue in the cycle. We always take the best option we have and spend as many defenders as we can on this option. And it should be clear that this, if there are n walls, then the solution runs in n log n time, because each wall will be processed at most twice. Once for this regular damage, when we are spending as much as we can on the wall, and possibly once eating also the remainder. So there will be at most 2n steps of the computation, and for each of them we need log n time to extract the current option from the priority queue. Alright? Let me look at the constraints in the next problem. Okay, so the next problem I told you about is the problem break. We have a rectangular piece of chocolate. We are given the constraint that A times B is less than or equal than 10 to the 12. So it can even be a single strip of chocolate of value just 1 by 10 to the 12. And we are given a constant C that is less than or equal to A times B. And the question is as follows. We can break this chocolate into smaller pieces, always in each step taking a rectangle and breaking it into 2 smaller rectangles with integer dimensions. And we have promised to give our friend exactly C unit cells of the chocolate. We can give them multiple pieces. It doesn't have to be a single piece of C, it may be impossible under those constraints, so it can be in multiple pieces, but it has to be exactly C. And the question is, what is the minimum number of breaks we need? And this is a problem where the answer isn't immediately obvious, so we have to play around with it a little bit. So the first thing you should realize before writing any code is what is the maximum possible answer? What is the maximum number of breaks you may ever need? And one way of answering this question is as follows. Imagine that you start selecting the cells, the C cells for your friend, just in a row major order. So you will take a few whole rows and then a few additional cells. So for any C, we can create a shape that looks like this, and that has area exactly C. We are just counting one cell at a time until you have exactly C. And in order to give our friend exactly this part of the chocolate, it is enough to make at most 3 breaks. You break it here, then you break it here, and then you take this strip and you break it there. So the answer is always at most 3. And as soon as we make this discovery, now we know that all we need to do is we need to check whether the answer is 1 or 0. If C is equal to the boundaries, I'm not sure whether this was allowed. If yes, then sometimes the answer can be 0. It can be 1, it can be 2. And if there is no solution with 1 break and there is no solution with 2 breaks, then we don't have to do anything else, we can just output 3. So there can be a solution with 1 break, and there can be a solution with 2. What is the solution with 1 break? A, B, it looks either like this or like this. In this case, we are looking for x such that A times x equals C, which means x equals C divided by A. So the solution with the single break like this works if and only if A divides C. If this is an integer, then we have a valid solution with 1 break. The same goes for the other direction, but B has to divide C. So if either of these is true, we have a solution with 1 break. If neither is true, we need at least 2 of them. Now the 2 breaks are the most tricky part of the problem, because we have to realize the following thing. What you can do is, in 2 breaks, is you can break it either like this, but this makes no sense, because if you give them any 2 pieces, you could give them the same area, but by doing just a single break. If the both breaks are in the same direction, then you definitely can shift it in some way. If you give them, for example, this one and this one, it means that the total length here would be a divisor, and if you put it together and make just a single break, you get the same solution. So the only thing that makes sense is to break first in one direction and then break the other, one of the 2 pieces in the other direction. So a pattern like this. And now the tricky part to observe is that you can give your friend either in this area, well, or symmetry to this area, or you can give them 2 of the remaining ones. So either you make a smaller rectangle, so this was A and B, either you make a rectangle like this, A prime times B prime, and give them this rectangle, or give them the rest. The easiest way to implement this is to check both cases. So to check whether you can produce A prime and B prime such that the product is exactly C, or to produce them in such a way that this product A prime times B prime equals A times B, which is the entire area, minus C. So this would be C, and this would be the rest. So the only thing that remains is checking this. Given A and B, can you find A prime and B prime such that they fit inside? So A prime is less than or equal to A, B prime is less than or equal to B, and their product is a given constant. And now you could do some kind of number theory or something, but you don't have to. Right now you can solve the rest of the problem by brute force, because if A times B is at most 10 to the 12, this means that the smaller of these 2 values is up to 10 to the 6, which is only a million. So, without loss of generality, let's assume that A is less than or equal to B, because we can swap them otherwise. It follows that A is less than or equal to a million, and it follows that A prime is less than or equal than a million. So we only have 1 million possibilities for the value A prime. And given that we already know A prime, and we already know the constant we want to have as the result, we can check whether this divides this, and if it does, we can compute B prime, and we can check whether it is actually less than B. So the rest of the problem is the easiest solution is try all possible values A prime, find those that produce value B prime, and if any of them works, you have a solution, and if none of them work, then you have tried all possibilities and you know that there isn't a solution. And that's it for the problem. Okay? Any questions? Everybody happy with the solution? Great. One thing I would like to highlight here, that is important about this problem in my opinion, is the conceptual switch that happens here at the end. So until some point, you are trying to solve a task on paper, you are starting to solve it as a mathematical problem. But at some point, the best solution is to realize that right now the number of possibilities we have left is small enough for the computer to examine. And as soon as this happens, it's usually the best idea to actually do so, let the computer do the work for you. Because if you continue solving it by hand, it may be hard, it may be too complicated, and you can make mistakes. If you let the computer examine all possibilities, you are sure that it will not miss the solution, because if it's there, it has to find it. So, when solving problems like this one, this last step should actually be your goal. You are trying to analyze the problem until you get to the point when the number of remaining possibilities is small enough to use brute force. Sometimes it may be at the very beginning, you just need to look at it from the right side. Sometimes you need to do a few steps manually, like here, to get to the place where you can afford to do the brute force. Alright, so next easy problem, the problem called STEM. We have a large piece of paper with some black and white pixels. And we also have a smaller rectangular pattern, which is a stem. We know that the stem is covered by ink. And whenever we take it and place it anywhere on the paper, all of these cells will change from white to black. So we are given these two bitmaps, a large bitmap of the paper, a smaller bitmap of the stem. And the question is whether or not it is possible that the pattern on the paper is the result of multiple disjoint applications of the stem. So the actual rectangles are allowed to overlap, but each of the cells on the rectangle of the paper can be stamped at most once. So the black ones have to be stamped exactly once, and the white ones can never be stamped. What can we do with a problem like this one? One thing we can do is we can start as if reading the paper row by row until we hit the very first black pixel. Another thing we can do is we can start reading the stem row by row until we hit the very first black pixel on the stem. And now the crucial idea of the entire solution is that these two pixels must match. Why is this the case? Well, because this pixel has to be covered by some of the pixels on the stem. And if you use any other of the black pixels to place it here, then this particular one will appear higher, or farther to the left if there would be a second black pixel here, and you say that this is this one, and this one will appear here. And which is anyways in the area we already examined and make sure that this doesn't contain any black pixels. So the only viable solution is that the first pixel we encounter on the paper has to be the first pixel we encounter on the stem. And that gives you the complete solution. Because what you can do now is you can go through the rest of the step, find all of the black pixels here, verify that they are here on the paper, and then you can undo this particular step. So you can change all those black pixels into white ones, and then you can simply continue on. So we found one occurrence of the step, we removed it from the paper, and now we have the same question. There still remain some black cells. Can they be produced by using copies of the stem? It is the same question. We continue with the same algorithm. So that's the entire algorithm. Now the only question is how to implement it efficiently. So first of all, now when we are going to continue the search for the next black pixel on the paper, we will not restart it from the top. Instead, we will continue from the place where we just stopped. So we know that everything here was white, and it remained white after we undid the stem. So we can just continue on from here. So in the actual implementation, this looks like, for example, the solutions when we are using multiple iterations of breadth-first search to find the individual connected components. So we will have two outer cycles, overall rows, and within that overall columns that go through this bitmap. And whenever you encounter a black cell, you call a subroutine to undo a step, and then you continue on from the point. So the first optimization is this. The outer cycle will therefore go through the entire paper exactly once. So this is linear in the size of the paper, except for one thing. And the one thing is that at some points, whenever we encounter a black pixel, we'll be calling the subroutine undo a step that has the black pixel here. What can we do with this subroutine? Again, we cannot afford to traverse the entire stem over and over again, because the stem can be also large, and there can be just a few black pixels. But to give you a specific example, if you have a paper that is completely black, and then you have a stem that is completely white, but only has a single black pixel somewhere here, you cannot afford for each of these black pixels to process these white pixels uselessly over and over again, because it will time out. Your time complexity would be the area of this times the area of this, which is too much. So the easiest thing you can do is you can pre-process the stem. You can go through the entire stem, one row at a time, at the beginning of the algorithm, before you do anything else. And what you can do is you can collect the coordinates of all the black cells on the stem. So instead of having a bitmap of the stem, we will just have two vectors of coordinates, row and column of each of those black cells on the stem. And now whenever you call the subroutine undo a stem, what you do instead of going through the entire bitmap is you go through the list. So you know the exact coordinates where you expect the black pixels to be, and only two things can happen. One of the things that can happen is that you successfully find all of the cells to be black also in the picture, in which case you can color all of them white. And the other thing that can happen is that you find a mistake, that you will find that the stem goes outside of the paper, or you will find that this cell is supposed to be black but it is white. And if this happens, you can immediately break the entire solution and you can output that it's impossible. So the slowest part of the solution can be the part where you undo the entire step and you go on. But the thing to realize here is that this will have a very good time complexity, because for each of the cells on the paper, you only change it from black to white exactly once. So even if there are many cells on the stem, it means that if we are successfully undoing the stem, we are changing many cells from black to white at the same time. So if you had a solution, if you had an instance, an input, where the answer was yes, the answer was that it's possible, then what happened during the solution is that you went in the outer cycle, went through the paper exactly once, and in all of the iterations of the inner cycle together, so in all of the cases when you call the function now remove a copy of the stem, then together all of these functions only cover the entire paper exactly once. because each of them removed some different collection of black cells, and those were all disjoint. So by eliminating the unnecessary white cells from the stem, by only processing the black cells every time, we improve the time complexity, and it is no longer this area times that area, but it's only this area plus this area, which means it's linear in the size of the input, and that's the best we can get. Okay, so that's the problem stand. Everybody happy? No questions? Makes my life much easier. But I'm not here to have an easy life, so if you do have any questions, don't hesitate to ask.
Wilson, just the last step you said that it's not more the multiplication but plus step y.
Okay, let's see it on a simpler example. So let's say that the stem looks like this. These cells are red, and these cells are all white. Now what happens is that whenever, so if let's consider two cases. First of all, let's consider a case that this is a valid solution, so we will have the answer yes, and then we will consider the case when the answer is no. If the answer is yes, then this means that there are some disjoint copies of the stem here on the paper, like this, and so on. And now, whenever we find a black cell, we call the function remove the copy of the stem, and the first call of the function will take 4 steps, and we'll change this from black to white. The second call of the function will take 4 steps, and we'll change this from black to white. And the next call will change this from black to white. And each time we are changing a copy of a stem from black to white, we only take the time proportional to this particular stem, to the number of cells we are changing from black to white. So the total time spent is at most the entire area of the paper. So this is if the answer is yes, and if the answer is no, the only thing that changes is that you will break it sooner, because as soon as you find an empty cell here, you will not process the rest, and you will just say no. So it's even faster. Okay, we have a pretty good pace so far. Let's do 2 more easy problems, then we can take a break, and after the break we'll look at the hard problems. Well, easy and hard are obviously relative. So easy means that enough teams still could solve the problem. So the next problem we'll take a look at is the problem track. So in this problem, we have a directed graph. And each of the edges of the graph has some possibly positive, possibly negative weight, and the value is called profit. So we like the large numbers, we like to have a large profit. And what we are asked to do is that it is our destiny to travel along this graph indefinitely, forever, and we want to maximize the profit per step. So we want to find an infinite sequence of steps in this graph such that the limit of the profit per step is as large as possible. Clearly, there is a much easier way of saying the same thing, and the reasoning is as follows. If you have an infinite wall in the graph, there must be cases when a vertex repeats. There is only a finite number of vertices, so you have to revisit some vertex multiple times. And if you have in your random walk, you have different occurrences of the same vertex, like this, and like this, maybe this is some W, and there's some W later on, and there's some W even later on, and so on. Then what you can do is you can look at each of these subsequences. So this is a piece of the solution in which no vertex repeats and ends in the same vertex. And what you can do is you can compute the profit per step just for this segment. And if you do this, there is only a finite number of segments, and one of them has to be the best one. And it makes no sense to repeat different sequences of vertices that are worse than this. So it's quite easy to show that the answer is always equal to the best cycle in the graph, a simple cycle you can get. So once again, the reasoning, because I think I didn't say it clearly enough. If you look at any solution, the solution will contain some cycles. For each of those cycles, you can evaluate how good it is. So you can take the sum of its edges divided by the number of those edges. And one of those cycles has to be the best one. And the optimal solution is then clearly to ignore the other cycles and to just go around the best cycle you can find. Because you cannot get a better profit per edge anywhere else. So we could rephrase the entire task as follows. You are given a directed graph, and there can be arbitrary edge costs, and you have to find the cycle with the maximum average cost. So how can we do this? It looks kind of like a shortest path problem, but not entirely. First of all, there's the maximum but not minimum. Well, this is something that can be dealt with. We can also look for the one with the minimum by simply negating the costs of all of the edges. So if you prefer minimum, we can have minimum. We just do minus x instead of x on all of the edges, and then we look for the one with the minimum. So this will be okay. The problem here is that the shortest paths aren't really what you need, because, for example, you can do something like, in the original problem, the longest path. If you can do something like this, 10 and 10, then this is 20. But it might be better to do 19, because here the sum is 20, but the average is only 10. You are increasing the count by 2. And if you go down like this, use 19, then you are increasing the count, which is only by 1, so the average you use this edge can be better than the average you use those edges. So just looking for the longest paths isn't exactly what will help you. Yeah, Bellman Ford is a very good keyword. So we can compare paths as long as they have the same number of edges. If you have two paths and each of them has exactly k edges, then the answer is clear, because if you have a way of getting from here to there in 3 edges like this, and you have another way like this, then now you can say that the one with the better profit is clearly better, because regardless of how you continue, you have the same number of edges and you want to maximize the sum. So as long as you can keep the number of edges constant, then you can simply take the path with the maximum sum, and this is the one you need. A slightly different way of looking at the same thing is as follows. We know that whenever there always has to be an optimal solution that is a simple cycle, a cycle where no vertices repeat. Because even if you have a solution that looks like this, that goes through the same vertex multiple times, then either this half or this half has to be at least as good on average as the average of the entire path. So you can take just one of them, and in this way you can reduce any cycle to a simple cycle that is at least as good. So there is always a solution that is a simple cycle, which means that it consists of at most n edges. And now we can start asking the questions: what is the best cycle with a single edge? So this would be a sample of maybe. What is the best cycle with 2 edges? What is the best cycle with 3 edges? And all the way up to what is the best cycle with exactly n edges. And if we can answer these questions, we know that the optimal solution has to be the best of those. So these are the questions to answer, and Bellman-Ford is one of the ways to do so. So what can we do now is essentially dynamic programming on the graph. We will start by trying all possibilities for the starting vertex. So we have a graph. We have fixed the starting vertex, and now we initialize the area of distances. And the area of distances will look as follows. If we start in vertex V and we want to end in vertex V, the best profit we can currently get by taking no edges is 0. And for all other vertices, it is impossible to be there, so it's impossible to have any profit. So the others are initialized to minus infinity. And now we do the dynamic programming, now we do the Bellman-Ford algorithm. So this array tells you for each vertex what is the maximum profit we can get if we start at V and use exactly 0 edges. And now we will use this array to compute such arrays for 1 edge, for 2 edges, and so on. So the general step looks as follows. Suppose we already have such an array for I. So for each of the vertices, for instance for the vertex W, we know the best way of getting there from V in exactly I steps. And this is precisely when we are like classifying all of the paths, or more precisely all of the walks on the graph, by the number of edges. So the value here in column W is the maximum taken over all possible ways of getting from V to W in exactly I steps. And now we have this maxima for all of the vertices, and what we can do now is we can go from this array to the array for I plus 1, simply as follows. We initialize this to minus infinity, and then we process all of the edges in the graph. In an arbitrary order, we can just look at each edge one at a time. And whenever we encounter an edge, for example, an edge from W to X of profit 7, what we can do is we can take the best way of getting here in I steps, which is this value. We can add 7, and we have found some way of getting to X. So we take the rule with X, and we compare this value to this value plus 7. And we take the value of those. So what happens here is that you take all the best solutions that have exactly I steps, and you try all possibilities of appending the next edge to each of those solutions. So you could implement it like for each vertex, for each W, you explicitly try all of the outgoing edges and increment those things. But you don't even need to store the graph in memory. You just need to store the list of edges and to go through it in any order, because you will process those edges anyway. So the implementation is really easy. Going from here to there is just one single for cycle that goes over all edges of the graph. So each of these steps takes all of n time. And we do this starting from 0 and ending at exactly n. So for each of the length, each of the numbers of steps between 0 and n inclusive, and each vertex of the graph, we have computed the best way of getting from this specific chosen vertex V to that destination vertex. Now the thing we are actually interested in are cycles, in particular cycles that include the initial vertex V. So for each of the lengths, for each of the number of steps, what we do is we look at this column, the column that represents vertex V. So what we have here is the best possible profit from starting at V and getting back to V in exactly I steps. And if the optimal solution includes the vertex V, it has to have some specific length, some specific number of steps, and this means that in one of these rows we will discover it. So what you take now is you take all of these values, not the zero value because you don't want to divide by 0 and it doesn't work anyway. So starting from 1 all the way to n, you take each of these values, you divide it by the corresponding number of steps, and this is the best solution you can get in that number of steps, and the maximum of those values is the best cycle that contains this particular vertex V. Okay? Does it make sense? So for one specific vertex V, we do this one iteration of the Bellman-Ford algorithm, and the running time is this. So the initialization is an n, but then the most time-consuming part is that we are doing n steps, and each of the steps takes O(n) time. So a single iteration of Bellman-Ford will be n times n. But what we have to do is, in order to find the best solution to the entire graph, we have to do this time and time again, always choosing a different version, different vertex V as the starting vertex. So we have another factor of n in the time complexity of the solution. So for each vertex V, and for each I, we will compute the best path to all the other vertices, including V itself, and this gives us the solution. So we have tried some possibilities for the path, and we are sure that the optimal solution is among them, and we can compute it in this time complexity. So this is a complete solution that's fast enough and correct and everything. Okay, are we happy with this solution? Yeah?
Did you say there can be negative edges?
Yes, and they don't matter for Bellman-Ford. The algorithm works for arbitrary costs.
Yeah, I just read in the text that they can only be greater than 0.
Okay.
Okay.
Yeah. The solution would still work even if they were negativities. If they are all positive, the better. Okay, so this is one way of solving the task. And there is also another way that has a similar but different time complexity. And the idea is as follows. One thing we can do with graphs is we can detect the presence of negative cycles. So for example, if you do Bellman-Ford algorithm to find the shortest paths, so that you're not taking the maximum as we did here, but you're taking the minimum in each step, what will happen to you is either after n-1 iterations, everything converges, and you already have the shortest distances from the chosen starting vertex to the rest of the graph, or there is a negative cycle that is reachable from the starting vertex, and in that case, the algorithm will never terminate. Each iteration will update at least one of the cells, and forever, as you are going around the negative cycle, you are improving some of those distances. So in this way, Bellman-Ford can be used to detect the negative cycle reachable from the chosen starting vertex. But maybe an even easier way of doing so for the entire graph at the same time is to use Floyd Warshall. So in Floyd Warshall, what you start with is a matrix of distances that has zeros on the diagonal. And if the graph contains some negative edges, then there can be negative values somewhere in the matrix. And now if you run the entire Floyd Warshall algorithm, what happens if the graph doesn't have any negative cycles, then you will get the new matrix with the shortest distances, and the diagonal will still be all zeros. And if the graph does contain negative cycles, then for each vertex on the negative cycle, the algorithm will encounter a way of improving this value by traveling from this vertex somewhere else, and from somewhere else back to this vertex again. So as soon as there is at least one negative cycle in the graph, the diagonal will change from zeros to some negative numbers, because we will find a way of re-entering the same vertex at a cost that is below 0. So you can use Floyd Warshall to detect the presence of a negative cycle in a graph. You run the algorithm in n cubed time, You check the diagonal. If it is all zeros, there are no negative cycles. If there are some negative numbers, there is a negative cycle. So we have a test like this. How can we use it to solve the original problem? So we have a graph with some cycles. And the thing, okay, so for simplicity, so that I don't have too many different signs in the same formula, let's assume that we took our original problem when we are looking for the cycle with the maximum average, and we negated all of the edges, so that now we are looking for the cycle with the minimum average. And now we can ask the question, so directly computing the best cycle can be hard, but we know one useful technique how to change an optimization problem into a decision problem, which is binary searching the answer. So we will ask the question, is there a cycle with average less than or equal to x? Or maybe, let's make it strictly less than x. So we ask this question, and how can we answer this question? So we have the original graph with some edge costs, and if we want to ask this question whether there is a graph with an average less than x, what we can do is we can subtract x from each of those costs. What happens now? If we had a cycle with an average less than x, now the average is less than 0, because we subtracted x from each of these edges. So you had a cycle that had profit 1 plus profit 2 plus profit 3 divided by 3, and this was less than x. Then now if you subtract x here, and x here, now you get p1 minus x plus p2 minus x plus p3 minus x divided by 3. And you have exactly 3 copies of the x because each of the edges have changed. So this is the original average, p1 plus p2 plus p3 divided by 3 minus x. And if this was less than x, this new value is less than 0. And vice versa. So the original graph contained a cycle with average less than x, if and only if the modified graph, where we subtracted x from each of the edges, contains a negative cycle. And that's it. So what we do now is the entire solution is a binary search for the optimum value of x. And inside the binary search, we always use a call to the Floyd-Warshall algorithm on the current modification of the graph to verify whether or not there is a negative length cycle. So in this way, we will find the optimal value of x, and we can output it. So the time complexity of this solution is nq times logarithm of the required precision. So this is essentially a constant, because after finitely many iterations, we will get the answer precise enough for our needs. In particular, it will not change anymore because the precision of the doubles will be exhausted. So if you do something like 100 iterations, you should already be safe and have an answer that's as precise as possible. If you really want to have an exact solution using this approach, you can always realize that the actual answer is a rational number, it's a fraction, and the denominator is very small. So you can binary search not on real numbers, but on the set of all fractions with small denominators, and then you will have an exact solution for this problem. But that's an overkill, that's not necessary. So it's much easier to do everything in real numbers. You don't even need to care about some precision issues, because the precision issues will be addressed by taking x that is slightly larger or not. So you can just use doubles everywhere, without any rounding, without anything, without any epsilons, and just do all the calculations of doubles and do all the comparisons exactly. And it will converge anyways because it's numerically stable, obviously. So two different approaches. The first one was completely discrete, and it would go on 4 n squared n times n squared. But there's also this other approach with for partial and looking for a negative cycle and binary searching. So two different solutions to the same problem. Alright, let's do one more problem and then we will take a break. The next problem is a problem called movies. So there is going to be a movie marathon. A girl can enter the theater and look at as many movies as she wants, but she has to do a continuous sequence of the movies that are being shown. And she only likes a movie if she sees it exactly once. So we have a sequence of numbers. These are the movies that are being played. Something like this. And each of the movies has an associated profit, associated value we get if we see the movie exactly once. And now the question is, what is the optimal interval of the movies we should see, the interval that will give you the best feeling? So it should contain unique movies with the maximum sum of those good feelings, and the other movies that occur there 0 times don't matter, and the movies that occur all at once also don't matter. So the first possible solution that is obviously way too slow would be to solve this in something like cubic time. Just brute force over all possible subsequences, and for each of them go from the left to the right, keep track of the number of different movies, keep track of the score, and you have the solution. Obviously, this is an overkill because we are doing the same work over and over again. It is enough to brute force all of the possible beginnings. If we start here, then we can simply start the simulation at this point, so we haven't seen anything, and start. Here's a movie number 3. We haven't seen it before, so we get plus the benefit from the movie. We get plus the benefit from movie 47, plus the benefit from movie 5. And now we are seeing movie 3 for the second time, so now we lose the benefit from movie 3, so that's minus the same benefit we got in here. So at this point, we have only these two. Next we move here, and we are seeing movie 3 for the third time. And now, this doesn't change our score at all. Movie 1 will increase our score, movie 2 will increase our score, movie 1 will decrease it, and another copy of movie 1 will not matter. So what we can do is, for a fixed start, we can go from the left to the right like this. We can maintain our current score, and also maintain the set of the films we already seen once, we already seen twice. And we can use these to compute for each position during the same pass, what is the optimal solution if we stop here. So this would give us a solution that runs in quadratic time, or maybe n squared log n if we are already using an order map or something, but it can be implemented in n squared. This is still way too slow, but at the same time, this also gives us the idea of what is going on. So let's go all the way to the beginning, and let's imagine that we just did this simulation. So the girl entered the hall here, and we simulated what would happen as she stays for more and more of the screenings. And what would actually happen would be, here she would get plus P1, plus P2, plus P3. Here it would be minus P1, minus P3, plus P47, plus P5. Nothing, because we already had plus P3 and minus P3, nothing. We already had also plus P1 and minus P1, so nothing. Here it will be minus P2, nothing, nothing. So this will be the outcome. And now, the best solution, if we start here, is the best of the prefix sums of this sequence. So it's either 0 or 0 plus P1 or 0 plus P1 plus P2 or 0 plus P1 plus P2 plus P3 and so on. So the best answer for this beginning is the maximum prefix sum of these values. Okay, so far so good? Now let's see what exactly changes if we move the beginning one step to the right. The thing that will change is that right now we don't see this particle screening of movie 1 anymore. So the remaining movies will remain unaffected, and the only thing that will change is that the benefits of movie 1 will shift by one screening of this particular movie. So this screening will change from minus P1 to plus P1, and the next screening will change from nothing to minus P1. And additionally, we can change this to 0. So by changing this to 0, we are essentially saying that, yeah, we can still start at the very beginning, but now this movie will not give you any profit. So the only thing that changed are 3 individual cells in this sequence. Almost everything remained the same, only 3 of the cells changed. This screening started giving us profit, the next screening of the same movie gave us the profit, and the next screening of the movie that previously didn't do anything now takes the profit away. And after we make these 3 changes, we again ask the same question. What is the maximum prefix sum in this sequence? And this is the entire pattern of the solution. So we always shift the beginning one step to the right, which will induce at most 3 such changes. And then we ask the same question, what is the maximum prefix sum? Make 3 changes to the array, find the maximum prefix sum. Make other 3 changes, maximum prefix sum, and so on. So this is a set of operations we need to be able to perform in an efficient way. And probably the easiest way to do so is to use an interval tree, segment tree, range tree, tournament tree, whatever you prefer to like and to call it. This very simple data structure. So we build it like this. And now in each of the nodes, you can store, for example, 2 values, and the values will be as follows. So here we have a node. The node corresponds to a subsequence, and we will store 2 values. The first value will be the sum of the subsequence, and the second value will be the maximum prefix sum strictly within this sequence. So ignoring anything what happened before, the maximum prefix sum within this sequence. So if this is say the sequence 1, 2, or 1, minus 2, 3, and minus 7, then the maximum prefix sum would be here, which is plus 2. How do we update these values? Well, if I know the sum and this here and the sum there, I add them together and I have the sum in this vertex. And if I know the maximum prefix sum here and the maximum prefix sum there, then for the entire segment, either the maximum prefix sum is the one in the first half, so I can directly take this value, or I can take this sum, so the entire segment like this, and then the maximum prefix sum in this other part. So the second value here is the maximum of this value, and this plus this, right? And all the way down at the root, the second value, the maximum prefix sum for the entire sequence, is exactly what I'm interested in, is the current best profit from the screenings. So the entire solution looks as follows. I start by reading the sequence and doing the first pass manually. So I will go just through from the left to the right through the entire sequence, and I will generate all of these values. And just for a better way to process them in the future, what I will do is I will take all of the screenings of the movies, and I will divide them into buckets based on the number of the movies. So essentially, for each of the movies, I can create a queue with indices of the positions where the movie is being screened. Why is this useful? Well, because then I can simulate each step efficiently. So then what I will be doing is this shifting of the beginning. So each time I shift the beginning by one, I look into the original sequence to see the name of the movie. I look into the array for this particular movie to find these three indices. All of this I can do in constant time. Now I will make 3 changes to this array. And after each change, I will recompute the path in the interval tree. So that making the 3 changes can be done in logarithmic time. And after those 3 changes, again in constant time, I see the best solution for the current beginning. So to summarize the entire solution with the time complexity of n times log n, because we try n possible beginnings, and for each of them we do 3 updates, and each of them takes log n times. So problems like this one are quite tricky because the hard part is making this observation, to take the original problem and actually change it into a data structure problem, change it into a problem where each step introduces only a small finite number of changes. So I do consider this to be a hard problem, and you need non-trivial experience in such problems to be able to solve it. There are some tricks, there are some patterns that do occur in tasks from time to time. One other thing I would like to mention is that sometimes you get problems that look similar to this one, that have queries of the type like, given a range, tell me the number of distinct items in the range. And the trick there, how to solve it efficiently, is that for each value, for each occurrence of a value, we can then store not just the value, but also the index of the next occurrence. And then if you have a range, so you have an array, the array, you get a range query, and within the range there are several occurrences of the same value. Then what happens is that for this value, the index of the next occurrence is still within the range. For this value, the index of the next occurrence is still within the range. But for this value, the index of the next occurrence is already outside of the range. And so this value is then the only one you count as the occurrence. So in order to answer a query about the number of distinct items within the range, you can count those items within the range that have a second value larger than the upper bound of the range. This is a standard trick that sometimes occurs in problems similar to this one. It's a different problem because in this problem we only wanted those that are unique. But if you have a very similar question, the number of different items, so discarding duplicates, then this is a trick how it can be done. But many of these questions can also be hard. So sometimes if you are just thinking about related problems on your own and you don't have a guarantee that there is a solution, then if you start asking questions similar to these two, you can very easily ask questions that don't have any efficient solutions. So we are mostly at a place where there is a collection of small tricks that sometimes work for special cases. And this happened to be one of those special cases when there is an efficient trick and you just have to apply it. Alright, questions about this one?
Yes, I do not understand how do you calculate the maximum prefix sum.
Yep, let me try it again. So, suppose you have a sequence like this, and you already know that within this part of the sequence, if you start here, the best place is to end here. So this is the maximum prefix sum for the first half. You also have the information that if you start here, the best place to stop is there. So just for the second half, independently, this is the maximum prefix sum. Now if you make the entire sequence, so you have to start here, Then one possibility is that the best possible end is here. So if the optimal end would be in this part, it has to be this one because nothing changed. So this is the first candidate for the solution. And the second possibility is that the optimal end is in the second part. But if you end in the second part, you are definitely taking the entire first sequence, and then you are taking some prefix of the second sequence. And we already know that the best prefix of the second sequence is this one. So there are only two candidates for the solution. Either is the best prefix in the first half, or is the sum of the entire first half plus the best prefix of the second half. So you only take the best of these two, and this is the answer for the entire sequence. So this is what I was saying, that when you're computing the value here, you will either take this value, so the maximum prefix sum for the first half, or you take the sum of the first half plus the maximum prefix sum for the second half, and the better of those two.
I got it.
Alright. So, a well-deserved break of 10 minutes. See you afterwards.
Isso não dá pra ver agora. Isso não dá pra ver.
Senão seria bom pegar tudo agora.
Porque, por exemplo, às vezes tem que dar um negativo.
Mas aí teria que ser a gente pegar tudo.
Porque para você ter que pegar o que tem antes, tem que ser um prefixo. Você não pode.
Mano, não curto som, sério. Sem confiança.
Alright, so we have, I think, 5 problems left to go from yesterday's session. Today, well, sadly, after the contest, I did write at least very short sketches of the solutions of problems from today. I will email them for Enzo and we can distribute them to the rest of the camp so that you will have at least some idea how to solve the problems of today's session. And also like during the dinner, if you have any specific questions about those, then feel free to ask me. Right now, I will just go through the rest of the session yesterday. And we can start, for example, with a problem about exploring Mars. Now, what we are doing in this problem is a grid of arrows, as if, and each of those arrows points to some other cell in the grid. And these arrows will necessarily form some cycles. This is because they are not allowed to point outside of the grid. For the actual solution to this problem, the fact that the input is a grid doesn't matter at all. The solution will be the same for any graph with the same property. So this is a very specific type of a graph. This is a directed graph without degree 1. So from each vertex, we have exactly one outgoing edge. We can have multiple edges like this coming into a particular vertex, but each vertex has exactly one outgoing edge. This makes the travel along the graph deterministic, because wherever you are in the graph, you have exactly one option where to go next. So these graphs are very special, and they are kind of easy to process. In particular, many problems that are easy on trees can also be solved on graphs of this type. It's kind of a similar generalization as there would be cactus graphs for the undirected case. In the undirected case, like a meta theorem about cacti is that whatever you can solve on trees, you can also solve on cactus graphs. It's just more difficult. The meta theorem is not completely true, but often we will see, especially if you practice on Russian contests, you will see problems that generalize algorithms from trees to cactus graphs. And this is slightly easier, but it is also some kind of generalization of a tree. So let's imagine that you start anywhere in such a graph without degree 1. And you follow the edges. So you are visiting vertices as you go. And you have the option of going on forever, but the number of vertices is only finite. So after some time, the vertex has to repeat. So regardless of where you start, eventually you will reach a cycle. And from this point on, you will just keep on going around the cycle. And this tells you the general shape of these graphs. Each graph that has out degree 1 consists of a collection of such cycles. And for each of the cycles, there can be many incoming paths into the cycle, and they can even meet before they reach the cycle. So in general, you can view each connected component of the graph to be a single cycle, like a terminal cycle, and in each vertex of the cycle, there is a whole tree of incoming paths. So this is the general structure of graphs like this one. Now that we know this about the graph, we can go back to the actual problem. In the input, some of the spots in the matrix are designated drop zones, and you can drop exactly one Mars rover, so exactly one robot, onto each of these cells. And the goal is to, first of all, maximize the number of robots to drop, and second, give exact timestamps when should you drop each robot, given that the robots will continue to travel along the direction of edges, and they can never collide, they can never try to enter the same vertex at the same time. So this is the situation now. If we visualize it not as a grid, but as a graph like this, what we can see is that there will be a bunch of connected components. You can also have a cycle like this, and then you can have incoming edges into the cycle like that. And in this component, you can also have, for example, 2 possible drop zones. And now we have this visualization, we already know what is going on in the graph. We know what will happen to each of the robots. Regardless of where you drop the robot will go for a few steps, and then it will reach the cycle. And from there, the robot will forever loop around the cycle. So this gives you an upper bound on the number of rovers you can use. For each connected component, you can only use as many rovers as is the length of the cycle. Because as soon as you use more than that, the 2 of them are guaranteed to collide. So this is the upper bound. You can use at most as many rovers as the length of the cycle, and at the same time you can use at most as many rovers as the number of drop zones. So you compute the length of the cycle, you compute the number of the drop zones in the component, and you take the minimum of those 2. And it turns out to be the case that this necessary conditions is also sufficient. So you can always place the robots in such a way that they will not collide. How to do this? When you know the location of the cycle and you know the length of the cycle, you can just take an arbitrary subset of those drop zones of the maximum possible size. So if you have more drop zones than the length of the cycle, you just take as many as the length of the cycle. And now you will take, what you have to choose is an offset for each of the robots. So the ideal situation would be that after some finite amount of time, each of the vertices of the cycle contains exactly 1 of the robots. And then they will shift by 1, and then usually by 1, and then forever they will keep on looping, and all of them will be sitting in those vertices, and everybody will be happy. So this is what we are trying to achieve. And the way to do this is to imagine the situation at time 0. So you fix some vertex of the cycle, and you say that this will be vertex of the cycle number 0, 1, 2, 3, 4. And now for each of the drop zones, you will make a decision that at time 0, I want this robot to be in node 0, I want this robot to be in node 1, I want this robot to be in node 2, and I want this robot to be in node 3. So then you compute the offset at which you should drop the robot for this to happen. So for example, the distance from this vertex to vertex 0 is 3 steps, then you need to drop it at time -3, or at time -3 plus the length of the cycle, or -3 plus some multiple of the length of the cycle. So for each of the locations, you take the offset of the robot, and from this you can compute the constant time, the optimal time when you should drop the robot. So you take the offset, you take the distance from the place where the robot should be at a given time, and then from those to those you add the smallest multiple of the length of the cycle, so that the robot will actually arrive in a positive time step. So the information you need to compute all these things is you need to know the structure of the graph. So you need to know what is the length of the cycle you will reach from each of these locations, what is the actual cycle. The way I implemented this is that at the beginning I just construct the graph. So these will be vertices 0, 1 through 1, 2, all the way through r times c minus 1. And now for each vertex, for each cycle, the label of the cycle as if would be the smallest of the numbers of vertices on the cycle. So this will be like the canonical vertex for the cycle. And offset 0 means that at the multiples of the length of the cycle you are in this particular vertex. Offset 1 means that you are in the next vertex, and so on. Now what you can do is you can do a simple depth first search or a simple simulation, but it's easiest to implement recursively. So for each vertex, you will just imagine like coloring this graph normally. So you go through all of the vertices one at a time, and whenever you discover the vertex that hasn't been colored before, you will start the function from there, and either it will reach a vertex that has already been colored before, and then we know that we are in the same component, and when we know the distance from this to the canonical vertex of the cycle, then this is +1, this is +2, and we have the distance for all of these as well. Or if this is the first time we encounter the cycle, then we will go recursively like this until we revisit the vertex, and now we will fill the information for all of these as we are coming from the recursion. So in linear time, you can process all of the vertices, and now for each of the vertex you know which cycle it goes to, and also the distance from the canonical vertex on the cycle, and this is all the information you need. So in linear time, you pre-process the graph, then for each component you collect the numbers and the locations of the drop zones, you compare them to the location of the cycle, and then you compute the starting offsets for all those drop zones you want to actually use. So it's a lot of work, but if you take it one step at a time, each of those steps should be manageable. Like dealing with the graph, processing it, and computing the right information is probably the hardest part in terms of implementation. Okay, does this make sense? The questions? Okay, next. The problem about the donkey. So we have a moving blocks puzzle that looks like this. There is a collection of different blocks that can be next to each other.
Eu acho que é assim, quer dizer que
So in this problem, we are given two different configurations of the same collection of labeled blocks. So in the second, so this is a picture of the starting configuration, and in the second configuration, we are guaranteed that you have the same pieces. So piece one will have the exact same dimensions as in the first picture, but it may be located somewhere else. And you can shift all of these pieces horizontally, vertically, as much as you like. And the board, the box you are using, is very long, so you have a lot of space on the right, but there is a fixed height. And the question is whether or not it is possible to rearrange the pieces from the first configuration to get the second one. So in this case, if there is a small piece, you can just shift this one a little bit, and then it can go around like that. So what can you do with a problem like this one? Again, I will show you two different solutions that are conceptually a bit different. They use slightly different observations. Well, still the general idea of both is the same. So this is a problem about whether a single piece fits around another single piece. So for instance, if the height of the 3 plus the height of the 1 is strictly more than the height of the box, then you cannot push the 3 to the other side of the 1. They will always have to remain in this relative order. So for some pairs of items, the relative order is fixed, and for some of them it can change. And you need to find a way to represent this information and use it efficiently. So, the first solution, and this was also the first solution I came up with for this problem, looks as follows. Clearly, all of the operations with the pieces are reversible. So if you do some movement, you can always undo the movement by doing it in reverse. So there is no way to get stuck, to make a bad move that will break the solvability. If it is solvable, it remains solvable regardless of what you do. So we can move the pieces as we like. And one nice way of moving the pieces looks as follows. We'll start from the right, going to the left, and whenever we hit a piece, so we hit the rightmost edge of a piece, now we know that the way to the right is clear, because we already, so this, at the beginning, this is the first piece we hit. So what we do now is we take this piece and we shift it far, far away to the right. And then we do the same thing with the next piece. Now we'll do it with the 1, then we'll do it with the 2, and then we'll do it with the 5. So now what we get is we get rid of these like special cases where 2 boxes are completely or partially overlapping on the x-axis. We just chose one particular order for those items. So now we will have them sitting in the order 4, 3, 6, 1, 2, 5. This is an order we can produce. And we already have a half of the solution done, right? Because we now have them one piece at a time. And now we take a look at the desired final configuration. And here we will go from the other side. In the final configuration, we want to have, for example, the box number 4 right here. Or maybe, well, let's do another one for us. Okay, let's do box number 3. So the leftmost item in the entire desired configuration, if it is the box number 3, what does this mean? It means that we have to get it to be the leftmost of all the boxes. Currently it is here, and in order to become the leftmost box, so in order to go from the cache here on the right side, all the way through here, we have to be able to push it past all of these. And here comes the part where the solution becomes efficient by using a suitable data structure. Because what we are doing here is a maximum query. Here we have pieces, and the thing that matters is the maximum of their heights. If all of their heights are small enough for the piece 3 to pass through, then everything is alright. If at least one of them is too tall, in our case both the piece number 5 and piece number 1 are too tall, so if the maximum of these heights plus this height is more than this, then this cannot be done, and we immediately know that there is no solution. So these are the only 2 possibilities. We do the maximum query of this range, we compare it to the height of this one, and either we are able to move this, or we find a contradiction. If we can find a contradiction, we are immediately done. And if we are able to move this, what happens? Well, this piece disappears from the cache. We do actually physically move it, we place it here, and we are left with the rest of the array. Now if we want to move the piece 4 next, we will now be making this interval query, whether it can pass by all of these, but the 3 has already been removed. So even if there is a collision with the 3, we don't check it anymore because we replace it by an empty cell. And this is the entire solution. So we are looking at the final configuration from the left to the right. You are discovering the pieces you have to move, and always you find it. You make a maximum query to see whether you are able to push it past all of those. And if you can, you just remove it from the order and place it into the final configuration. Once again, the simplest data structure you can use is a range tree. You build a range tree, you can answer those maximum queries in logarithmic time. You can remove items in logarithmic time as well. So we need n log n time for the sorted sweep to produce this sequence. Then you can build the initial range tree in linear time, and then you can assemble the desired configuration one piece at a time, again in logarithmic time per piece. And that's the entire solution. Okay, everybody happy? Any questions, comments about this solution? Yeah. All right, so I promised you 2 solutions, so let's get to the second one. Instead of doing these shenanigans, one other observation we can do is we can divide the pieces into 2 categories, into tall pieces and short pieces. And if this is, I think, H, the tall pieces are the pieces that are strictly taller than the half of the entire board. So why is this classification useful? Because it tells us something about the movement of those pieces. If you have 2 tall pieces, you can never push one of them to the other side of the other. So the order of tall pieces is fixed. The tall pieces have to be in exactly the same order in both configurations. If this is not the case, immediately we know that the answer is impossible. The short pieces can be swapped arbitrarily among themselves. If you have 2 short pieces next to each other, you definitely can make them change places. So the short pieces don't influence each other at all. The short pieces can be considered independently. And this is another observation, different from the one we made in the previous solution, but this one will also give us an efficient way of solving this particular task. So we have tall pieces. We can make the check that tall pieces are in the correct order. And now we can consider each short piece independently, because the other short pieces, even if we place them already, they don't matter. We can always go around those. So for each short piece, what we have now is we know where it is within the order of tall pieces at the beginning. We know where we want to have it at the end. And again, we just need to do the range maximum query, whether we can fit it past all of these. So if we have, so suppose this is the order of the tall pieces, and now we have a short piece that is this long, and this is the entire height, then it does fit by these 3, but it's too tall to fit here and to fit there. So if the initial configuration has it here, and the desired configuration has it there, that's okay, because all of these tall pieces are short enough. But if we wanted to move it all the way through here, then it cannot be done, because in this range, the maximum is already too tall for us. The difference and the thing that makes this solution easier to implement is that in this case, all of the maxima query are in a static sequence. So we have the sequence of tall items, and this doesn't change at all. So we can just assemble all of these queries and answer it using sweeping, or do some simple range minimum data structure, range maximum data structure to solve this problem. Or we can build a range tree anyways, if we like this, and we are convenient in getting it implemented. So once again, to summarize the solution, construct the sequence of tall items in the first configuration, in the second configuration, compare them to check whether they are the same, and then independently for each short item, find where it lies in the first configuration, find where it lies in the desired configuration, make a range maximum query to see whether you can push it from here to there, pass the tall items, and you know that we don't care about the other short items. So this solution required maybe a bit more thinking. This, in particular, this step is a trick. This step is something that requires experience, that requires insight to see. But once you make the observation, you are rewarded with something that has maybe a slightly simpler implementation than the previous solution. Okay, so much for the donkeys. Everybody seems happy. So moving on. We still have 3 other problems. let's do the fake Hanoi problem next.
Você fez isso?
Many years ago, when I encountered this problem, playing around with towers of Hanoi, and I made this observation about the invalid configurations. It was, to me, like an enlightening moment, something, well, obviously the towers of Hanoi is a very well-known puzzle. I have known it since early childhood, and I knew that you can solve it in 2 to the n minus 1 moves. And I never stopped thinking about all those other configurations, and suddenly realizing that there are configurations that are valid in the sense that all of the disks are stacked properly on the pegs, but at the same time we will not see these configurations during the solution, was a revelation that yes, there's something more to this puzzle. It's not just mindless recursion of doing it like this, and then being done, but there is something else going on. The structure of the problem is kind of deeper. And we can easily see that there have to be many such configurations because, well, the solution, the optimal solution going from peg 1 to peg 3 has exactly 2 to the n minus 1 moves. So we will see exactly 2 to the n different configurations along the way. But there are exactly 3 to the n possible configurations of these because for each of the disks, if you are placing them from the largest to the smallest, you always have a choice of 3 different pegs. So in fact, almost all of the configurations are the invalid ones, the ones that don't occur in the canonical solution. And now the task was given such a configuration of disks, so one that is valid in terms of game rules, but not on the optimal solution. We have to change it to one configuration that does occur in the optimal solution, using as few valid moves as possible. And as this is a towers of Hanoi problem, it would be a travesty if the solution didn't involve recursion in some way. So it will actually involve many of the ideas of the original solution. One, so we are given a configuration that looks like this. And now we are asking the question, what is the optimal solution for such a configuration? And when trying to answer this question, we have to go about it in a kind of a systematic way. And one nice way of being systematic would be to start from the smallest piece. But the smallest piece is something that just moves around very often. And a much better idea is start from the largest piece, distance somewhere at the bottom. So let's forget about this configuration for a while. Let's take a look at the optimal solution. In the optimal solution, what's going on? At the beginning, the entire cover is on peg 1. At the end, the entire cover is on peg 3. And in particular, if you look at the largest disk, what is going on is that in the solution, you take the n-1 remaining disk, recursively you move them to the center to free the largest disk, and there is only a single move that involves the largest disk. And this is the move that moves it from the left peg to the right peg. So in any valid configuration, the largest disk is either on the left-hand side or on the right-hand side. So there are only 2 possibilities for the location of the largest disk in any valid configuration. And now, if we want to fix this particular configuration, we have 2 options. We can either fix it into a configuration that has the largest disk here, or we can fix it into a configuration that has the largest disk there. And the way to find the optimal solution is simply to try both possibilities recursively. For each of them, find the best solution for the remaining disks, and then take the minimum of those 2 choices. So let's see what happens. If we want to have the disk here, it's already there. So this is great. We don't have to move it at all. And we get the following question. Given these remaining 4 disks, fix them into a valid configuration. And in this case, the valid configuration is a valid configuration of the original game because, well, is it? Not necessarily. In the original game, the configurations that have the largest disk here are the configurations in the first half of the game. And during the first half of the game, what we are trying to do is we are trying to go from here to there with the remaining disks. So this is not the same game as before. Originally, the game was that all disks are trying to go from peg 1 to peg 3. Now we have n-1 disks, but we are playing the game of moving the disks from peg 1 to peg 2. So these are the precise arguments of the recursive call. Here we have a configuration of n-1 disks, and fix it to get a configuration in which we are moving the n-1 disks from peg 1 to peg 2. So in this case, the arguments for the recursive call would be n-1, denoting that we have a prefix of the original sequence of disks of just like n-1, and then 1 and 2, which are the numbers of the starting peg and the destination peg for the part of the solutions we are considering. So if we want to keep the largest disk here where it is, then the optimal solution is the optimal solution to the subproblem n-1 disks from here to there. The other possibility is moving the disk. So in this other possible solution, we want to construct a valid configuration that has the largest disk here. In order to do this, first of all, we have to get it there. In order to get it there, we need to take all of the remaining disks and assemble them onto the middle peg. And this is actually a different question, but one that can be answered easily using, again, dynamic programming. So you have a code that takes these disks and using the fewest possible moves, build a pyramid on this particular peg. This is an easy problem to solve, and I hope everybody here can solve it on their own. So we will call this as a subroutine. We will get the number of moves necessary to do so. So right now we have a pyramid here, and the largest disk is still there. Then we do +1 for moving it here. And now we have a valid configuration already. Or in general, if the starting configuration had the largest disk here, we could have now a situation like this. So if we started with the largest disk here, we wanted to move it there, then we have to go like this. Build a pyramid of the remaining disks here, then move this disk over there, but this is not a valid configuration yet. The valid configuration will have this pyramid in the middle, and that is actually the best thing we can do. So either we have to move the entire pyramid here, or we have to move the entire pyramid there. Both of them are valid, and both of them require 2 to the size of the pyramid minus 1 moves extra. So you do dynamic programming to count these moves, then you do +1, and then if you have to, then you do +2 to the n minus 1, or 2 to the k minus 1. And you do this recursively. So you start the entire solution by making the recursive call, all of the n disks, and we are going from peg 1 to peg 3, and each of the branches will either give you another recursive call of this type, or it will give you a counting problem like this that will already be solved directly. And this gives you only a linear number of states, so the solution works in an instant. The number of different states you consider will be only proportional to the number of disks. So this is a difficult dynamic programming problem because you need to draw a lot of pictures, play around with the problem, but the actual implementation should be reasonably easy. Okay, does this make sense? Are there any questions? Is everybody happy? Is everybody already hungry? Hoping to get lunch as soon as possible. But no, there is no lunch in your future. There are more problems. Only then, when you deserve it, you get some food in your bellies. We still have 2 more problems left. And the first of those two problems will be the problem about backpacks. Well, this is a pretty problem. It does have a knapsack already built in the name of the story, but still it's very hard to see the correct solution. So, in this problem, we have 24 items of different sizes, 100 backpacks of different sizes. The items cannot be divided, so each item has to go completely into one of the backpacks. Each backpack can contain arbitrarily many items. Question number 1 is whether it is possible at all to pack the items into some backpacks. And question number 2, if yes, what is the minimum number of backpacks we will need? So, with this problem, it is easy to start. There is a very easy observation you can make, which is the set of backpacks you will use. If you decide to use exactly K backpacks, then obviously the backpacks you want to use are the K largest backpacks. You have nothing to lose. You can only lose something if you use a smaller backpack, because if you replace a smaller backpack by a larger one and you put the contents into the larger one, it still fits. So we know that if there is a solution, the solution has the form that for some K, we use the K largest backpacks. So the first thing we can do is we can take all of the backpacks and sort them from the largest to the smallest. And now we are getting to the hard part of the problem, to the key observation, how to solve this. So, in order to discover an efficient solution, well, a solution that is more efficient than brute force search, let's try thinking about the problem in the following way. Suppose that somebody already came and arranged all of the 24 items into an order. So chose a permutation of those items. Don't worry that there are 24 factorial permutations, which is not a lot. This will not be an efficient solution yet, but it will be a correct solution. So somebody came, arranged the items into an order, and now what we can do is we can take the items in this order and fill the backpacks greedily. So we can start with the first backpack, we can place some of the items into the backpack until we get an item that doesn't fit anymore, and then we will try placing it into the second backpack and so on. And in this way, we will probably get a valid solution, and maybe if we are really unlucky and the order is bad or there is no solution, at some point we will find the item that is too large for any of the remaining backpacks, and we say that, well, sorry, this particular permutation didn't lead to a solution. So this is a greedy algorithm, and if you just choose a random permutation, it definitely doesn't have to be optimal. It is even possible that there is a solution, but the greedy algorithm doesn't find it because it chose a bad permutation. But the important thing to notice here is that there is always a permutation of items that will produce the optimal solution. So if a solution exists, you will find it for one of the permutations. Why is this the case? Well, you can just imagine having the optimal solution. It looks like this. So these are items 3, 7, 15, and these are items 4 and 11, and so on. Now, if you take a permutation that has items 3, 7, 15 in any order at the beginning, and then the items 4 and 11, and so on, and then you use this particular permutation, you'll create exactly this solution. So that's it. So, if there is a valid solution, the greedy algorithm will find it for one of the permutations. So now we have a correct but slow solution. We could solve it in 24 factorial times something small. Try all permutations, and for each of the permutations, simulate the greedy algorithm and find the best number of backpacks you get over all permutations. Now we have to improve this solution somehow. And how do we improve it? Now comes the most crucial observation of the entire problem. So imagine that you have a collection of objects. This is a subset of the entire set of items. And you try one order of these items, and you will fill the first backpack to some boundary, then the next item order to complete. So you fill the second backpack partially like this. So this was one option. But if you chose a different order for the same items, then maybe you were able to fill the first backpack all the way to the top, and in the second backpack you used less space. And now given these two options, clearly this one is better than that one. Because now if you take the remaining items, and you try to continue the greedy algorithm, if you were to continue it from this configuration, you will not get a better solution than from this one. Because anything that can be filled in here can also fit in here. This is a better solution because the amount of empty space in the large backpack is larger. So we don't actually care about the order in which these items are inserted, and we don't actually care about all of the possible orders of those items. We only care about the one order that will produce the best solution in this sense. So this is the main idea of a good solution to the backpacks problem. For each subset of items, we can ask the question, what is the best way to greedily pack this set of items? And the best way is defined intuitively, like primarily you want to minimize the number of backpacks you will open, going from the largest one to the smallest one. So if you use fewer backpacks, it's clearly better. And if you use the same number of backpacks, the better solution is the one with the maximum empty space in the last backpack. So this is the question we are asking, and the answer to all of these questions can be computed at the same time using clever dynamic programming. So we will process all of the subset of the items, starting from the empty set all the way through all the items. At the beginning, we know the answers. We then recursively compute them for larger and larger sets. I will show the details in a minute. And at the end, when we have the answer for all of the items, it's exactly the answer. If I try all possible permutations of these items, what is the best solution I can get? And we know that this is the optimal solution to our original task. So again, the question we are asking for any subset of items, what is the best result the greedy algorithm can get for these items only? So if I were to try all permutations of these items, for each of them I would look at the final state of the greedy algorithm, what would be the best of all of those states? And I know that for the greedy, for the rest of the solution, I can just look at the best one. And the recurrence is very simple. So the best solution for the empty set is 0 matrix used, or maybe you can have it like two special cases. You can have it that we open the first backpack, and the empty space in the first backpack is the entire volume of the first backpack. So this is the optimal solution for no items. We open one backpack, and it is still completely empty. And now if you have a set of items, so the general case, and we are looking for the best solution for these items, then very simply, one of these items has to be the one that is placed last into the backpacks. So for any order of these items and the greedy algorithm, one of these items will be the last one. So now what we can do is we can try all possibilities. What happens if this item would be the last one? And now comes the dynamic programming part. We take a look at the optimal solution for these items, and then we simulate the next step of the greedy algorithm and place the item there. So either we put it in, so here we got the information that currently the open backpack is backpack number 7, and the current empty space in backpack number 7 is this value. If this item still fits there, we are still in backpack number 7, and we have less space. If it doesn't, then we open backpack number 8, and we get this answer. So we try to take the optimal solution for these items, and then place the next item, and we do the same thing for each of those. And the globally optimal solution for this set of the items is clearly the best out of those 6 or whatever, how many possibilities. So essentially you can view this solution as simply recursive memorization. So I'm recursively trying all 24 factorial possible orders of those items. But after each step, so only the set of items that are still remaining matters, and for the set of items I'm looking for this solution. So instead of simulating the 24 factorial permutations one at a time, always after placing each item, I'm discarding all the possibilities I don't need. I try 6 possibilities here. 5 of them are suboptimal. I forget about those, and I continue only with the best from them. So the time complexity, if you have n items, is then 2 to the n, which is the number of states, times n, which is the time needed to process a single state. And for n equals 24, this is fast enough. So in my opinion, this is a very non-traditional task in the sense that this is a trick I have seen before, used maybe once or twice in my entire career. It's nice. It's kind of like the thing I like most about this problem is that it looks so simple, doesn't it, right? There's so few items, it has to go somehow. No, it doesn't. You need a clever insight like this one to solve it.
Yeah. Can you just confirm what is the best solution? Because you are looking for a solution that uses the least amount of backpacks, and among the ones with the least amount, you are looking the one with the largest empty space in the
last one. So the main thing to realize here is what are we gaining by introducing the intermediate step with the greedy algorithm? Because if you just take, so this is exactly where we solve the problem. Because the main problem we have, you directly try to solve this problem, and you will just well, okay, I have this set of items, I will try processing them one by one. But in general, we will have a situation where you have multiple backpacks open, in each of them there is a bit of free space, and now when you're processing the next item, you have multiple decisions where to place it. And this gives you an exponential state space. This will give you very many different configurations of empty spaces in different backpacks you can get. And this doesn't lead to an efficient solution. So we need to get rid of this notion completely, the notion that we will be filling backpacks back and forth and putting items into backpacks in different orders. And we will instead, we came up with this greedy idea that you are filling the backpacks one at a time, and as soon as you close a backpack, you are never going back. So you are putting some items into the first backpack, and as soon as the next item doesn't fit, the first backpack is closed and never will be reopened, as if it were full. So at any moment in time, you have only one of fewer states. You have some backpacks that are closed already, exactly one backpack that is open, so everything you need to represent this part of the state is the number of the open backpack, and in the open backpack you have some empty space. And as soon as you do this, you get the immense benefit that before you couldn't compare two configurations. You have 3 backpacks with some stuff like this, or you have 3 backpacks with some stuff like that, and you cannot tell which one of them is better. But if you do the greedy algorithm, then there is obvious which configuration is better. If you use fewer backpacks, it's better than using more backpacks, because in the other solution you already started using the backpack, and in this one you still have more empty room before them. And if they have the same number of backpacks, the more space you have left, the better for you. So if you have an order that was left with a large item here, and another order that just left a small item here, the second order is really better. So as soon as we do this, as we come up with this observation that I can actually, so there are many ways to construct an optimal solution, and among those there's always a way to construct it by simulating the greedy algorithm. And then I have a very small number of different states that I can compare them. So we made this observation, And now we can compare the states, and now we can clearly state that for a given set of items, if you fill it greedily, you can get many different configurations. If you start with k items, you can theoretically get k factorial different configurations. Probably not, probably there will be fewer, but theoretically it is possible that you will get k factorial different configurations at the end. And among those configurations, you are not interested in any of them except for a single one, for the best one of those. And now you can do this, that instead of going through all permutations, you just go through all the subset of items, and for each subset of items, you are just interested in the best configuration of the greedy algorithm for this set of items and any of these permutations.
Reason. All the following solution fail. We first order the backpacks by capacity. And then after we enumerate all subsets and make a pair bits of the max of the subset, total weight used and we order all the results produced and iterate from the largest to the smallest using 2 pointers. Start at the largest backpack and the other pointer start from the subset with the largest weight and iterate wherever we have weight equal or smaller than the actual backpack. We fill the backpack and store we do an OR of that mask, do an accumulator mask, and we search for the next subset that which don't intersect with the accumulator mask.
I think like that it is possible to write a solution that looks at least similarly, but I think the things you are describing will time out because there will be too many combinations of what to have in some backpacks and then what to place in another backpack. If the items are like smallish, you can have many items in the same backpack. You will have very many combinations of items in one backpack and in the other. So I think it may just time out if having too many combinations. But one other thing I would like to very quickly mention before moving to the very last problem is that we can also view this problem as kind of a shortest path problem. So at the beginning, you are in a situation that you haven't filled any backpacks and you haven't used any items. And now you are essentially the simulation of all of the possible permutations in the greedy algorithm. It's that you can view these states, the set of used items as vertices of a graph, and at each moment of the greedy algorithm, you have a decision to make. You can place the next item among the items you haven't processed yet, so these are the edges in the graph, and each of these edges will bring you again to some state at some distance. And the distance is measured like this. So primarily the number of backpacks you already filled completely, and secondarily by the empty space remaining. And you are looking for the shortest path from the configuration you haven't placed anything to the configuration you have already placed everything. So this can be seen also as a graph problem. Okay, so for the very last problem now, the problem about the order of fractions. This is a problem by my late friend Mihail Patrascu. He has been a great researcher and also great problem setter for contest, but sadly, some years ago we lost him to cancer. This is one of the problems he came up with. So essentially what this problem is asking you to do is an operation that is called order statistics. So converting between the ordinal number of an item and an item in the sequence. And the sequence on which we are doing this is the so-called Ferry sequence. So this is a sequence of all fractions in reduced form that have denominators between 1 and n inclusively. So we have a sequence of all possible reduced fractions with a limited denominator, and then in this sequence we want to convert between the index of a fraction and the value of the fraction back and forth. This is what we are trying to do. First of all, we need to realize that if we have fractions of the form numerator divided by denominator, and denominator is less than or equal to n, then even if we take only the fractions in reduced form, there is roughly a quadratic number of those, because we have n possibilities for the denominator and roughly n possibilities for the numerator. Not all of the fractions are in reduced form, but if you do some counting, it follows from the fact that the sum of 1 over k squared is, if you go to infinity, it's pi squared divided by 6, so it's a finite value. So this is the kind of a fraction that represents those composite ones. One of those doesn't matter which ones. So a constant fraction of all of these are irreducible fractions, and therefore we cannot afford to just generate all of them because there are too many. If n is 500,000 or something, then there will be way too many fractions for us to generate and then count one by one. So we have to come up with something more clever. And one possible way of solving this stuff, certainly not the only one, but maybe one that's very easy to implement, will be as follows. So suppose we have all of these fractions, let's call the set capital F, and we can now ask the following question. Given k, count all the fractions a divided by b in F, such that a divided by b is less than or equal to k divided by n. So this will be a helper function we will write. I will later show how to implement it. But first of all, let's consider this as a black box, and let's see how it helps us. If we already have this function and we can do this count in an efficient way, then we can do both operations quickly. So if you are converting a fraction to an index, the thing you can do, if you have a fraction like c over d, you will find the largest k, such that k over n is still strictly less than this. Then you will compute this count. So if you have the order of all possible fractions, starting with 0 over 1, ending with 1 over 1, the c over d is somewhere here, and here is k over n, possibly in a more reduced form. Then our function can give you this count. So you will call the function, count all of these fractions quickly. And then here you have k plus 1 over n. And within this range, we can afford to actually generate all of the fractions, because as the length of this range is 1 over n, for each denominator between 1 and n inclusively, there will be at most one numerator that will make the fraction fall into this range. So if we count these separately, we can then generate all the fractions here in linear time. We can sort them in log time, and we can explicitly count the index of the fraction c over d. So if we are going to fraction to index, then what we need to do is one call to the magic function and plus all 10 times log n to generate all of the remaining fractions and find the actual index. right? If we are going to index to fraction, we will do essentially the same thing in reverse. So, if you know the index, you can now use binary search to find this k. So you can evaluate any specific k by calling the magic function. And you want to find the smallest k or the largest k with this property. So you want the largest k such that the magic function returns a value that is strictly smaller than the index. You can do this by binary searching the correct k. So you need a logarithmic number of calls of the magic function. And once you do so, once you know the k, then you subtract this count from the index. Again, you generate all the fractions within this range, and then you count you index into the sorted list. So for these operations, you need log n calls, and plus again n times log n. So if we can make a call to the function quickly, both of these operations will be efficient. So now we need to come up with an easy, quick way to compute this count. And this is the very last step of the solution. And it looks as follows. So we will take an array, and the index into this array will be the denominator. And if you fix the denominator, so at the beginning, let's forget about the fact that some of the fractions are not in the reduced form. Let's count all of the fractions with this property. And that's really easy, because if you are given k, n is a fixed constant throughout the entire solution, and you choose a value of b, then you can compute the maximum a simply by moving the b to the other side and rounding down to the next integer. So for each b, you know the number of valid a's that will give you a valid fraction within this range. So you fill in these values into the array. But now you need to get rid of the fractions that are reducible. For example, if there is a fraction 1 over 3, you have counted it here with denominator 3 among these, but also with denominator 6 as 2 over 6, and with denominator 9 as 3 over 9, and so on. So you need to subtract this from all of these, and the way this is done is you simply go through the array from the left to the right. And now, each time you see a non-zero value here, so for example, here you would see a 1, then you have a fraction with 1 over 3 in the array. Then you take all of the multiples of this, and you subtract this value from all of those values. You have a 2 here, so this means that both 1 over 3 and 2 over 3 are among your fractions. And now you know that these are counted in all the multiples of 3, so now you go through the array and you subtract them. So this is in some sense similar to the C or ortho studies. Always you take a value and you subtract it from all of the multiples of the value. And it can be shown that if you are subtracting this one, you can subtract it from all of them. This one only every second item will be processed, for this one every third item, and so on. So the total work done here is proportional to the harmonic number times n. So this means that the entire function, if you do it like this, runs in n times log n. And at the end, the final values. So whenever you encounter a cell, the number here is already correct. So this is the already correct value of irreducible fractions with this denominator and in this range. And then you take all of these irreducible fractions and you discard all of the multiples of these fractions, of all the equivalent fractions, but with the larger denominator. So in n log n time, you can do this magic function that counts these fractions, and then therefore the full solution has 10 complexity n log n in one direction, and n times block square then in the other direction. Okay, so for one final time in this camp, I'm asking the question, is everybody happy with the solution? Are there any questions or comments?
I have a question.
Yep.
What about the problem? How long the weekends will be for how long time the problems will be online?
Well, the online judge should be running for the foreseeable future. I have no plans deleting or changing anything. So until there is some maybe like a backend change of the grader that will break everything in the future, the grader will remain running definitely for like the next year or so. So when you go back from the camp, you will definitely have a lot of time to go back and upsolve the problems. And also, like, if you run into trouble with the problems and you don't know how to solve it and you want to give up, then just write me an email, ask a question, and I'll try to get back to you. I might be very busy, so if you don't hear from me, try asking again. That's the best thing you can do. Alright, so it's been a thorough pleasure being here for this week. You've been a great audience, and I hope to talk to many of you also during this evening. Okay, so thank you for your attention.